12:23 p.m. Your liver just ran out of sugar. Not low, not running low. Gone, the last of it burned through your bloodstream in the past few hours, and now something ancient wakes up inside you. Something that has been sleeping quietly in your cells since the day you were born, waiting for exactly this moment. This is not a diet. This is not a cleanse. This is the oldest biological program on Earth firing up. And the humans who carried it, the ones who felt what you're about to feel across days, then weeks, then months, they are the reason you exist at all. What happened inside their bodies? Hour by hour. System by system. The answer changes everything you think you know about hunger, about starvation, about what the human body is actually built to survive. Stay with this, because somewhere around the 72-hour mark, something happens that nobody talks about, and it will quietly reframe the entire history of our species. Hour 1. The moment food stops arriving, your pancreas notices first. Insulin drops, within minutes, not hours. Glucagon rises to take its place, and glucagon has one job: unlock the sugar that's been stored in your liver as glycogen and dump it into your bloodstream. Your ancient ancestors called this nothing. They didn't name it, they just woke up from a night's sleep or returned empty-handed from a hunt, and their body handled it invisibly, automatically, without asking permission. The liver of a typical adult male holds roughly 8,000 kilojoules of glycogen energy. That sounds like a lot. It is not a lot. It is enough to keep your brain fed for somewhere between 18 and 24 hours, depending on activity level, body size, and how much you are moving. 18 to 24 hours. That's one bad day of hunting. One failed overnight. One winter storm that lasted too long. Your ancestors hit this wall constantly. The difference between them and a modern person going 16 hours without food is that they had no guarantee of what came next. Hour 6. The liver has been burning through glycogen since the moment insulin dropped. Cortisol enters the picture now. Your adrenal glands begin pushing it out steadily. And cortisol does something that sounds harsh. It tells your muscle tissue to begin releasing amino acids. Specifically, it signals for alanine and glutamine to be stripped out of skeletal muscle and sent to the liver. The liver takes those amino acids and, through a process called gluconeogenesis, converts them into fresh glucose. Protein becoming sugar. The body eating itself to stay alive. This is where the word starvation starts to carry real weight. But here's what most people get wrong about this stage. Your body is not panicking, it is executing a plan. Gluconeogenesis is not a failure mode. It is the backup generator. It was always meant to run. The ancient humans living through lean seasons weren't spiraling into organ failure at hour 6. They were running the exact program that evolution spent hundreds of thousands of years perfecting. Their bones remember this. If you look at X-rays of prehistoric human remains from archaeological sites in the Arctic, Utqiagvik, in modern-day Alaska, you can see fine, faint horizontal lines running across the long bones. Researchers call them Harris lines. Dense growth arrest marks laid down in bone mineral when the body temporarily redirected resources away from growth and toward survival. The children who made these marks didn't die. They recovered. They grew. They carried those lines as permanent, silent records of the winters their bodies fought through. Starvation left its signature in bone, and those people survived. Hour 12. The hunger signal arrives in full force. Ghrelin, the hormone your stomach wall secretes when it's empty, has been climbing since your last meal. By hour 12, it's high enough to be noticeable as a physical sensation. A hollow ache, a restlessness. And here is where something strange happens that researchers at Rockefeller University and Imperial College London have both confirmed independently. Ghrelin doesn't just make you hungry. It activates the orbitofrontal cortex, the part of the brain that handles reward, planning, and focus. In a 2014 study published in the journal Cell Metabolism, researchers found that administering ghrelin to human volunteers produced measurable increases in hedonic response and cortical limbic reward cognitive circuit activation. That is the science version of saying hunger sharpens the brain. This is not an accident, this is a feature. Think about it from the perspective of 50,000 BC. What is the absolute worst time for your brain to go foggy, slow, distracted? When you haven't eaten and you need to find food. The body solved this. It wired the hunger signal directly into the attentional system. A ghrelin spike doesn't make you stupid. In the short term, it makes you faster, more focused, more attuned to your environment. The chill, relaxed, well-fed ones might have missed things. The hungry, alert ones didn't. Hunger is a cognitive upgrade. For a while. Hour 18, your glycogen is nearly gone. The brain, which runs almost entirely on glucose and refuses to compromise, is now demanding its share of a diminishing supply. The body responds by doing something ruthless. It shuts glucose delivery to most peripheral tissues entirely. Muscle cells, fat cells, skin. Glucose metabolism goes dark in those places. The remaining glucose gets rerouted. Brain, red blood cells, immune tissue. The hierarchy of priority is brutal and ancient. At this point, your respiratory quotient, the ratio of carbon dioxide your lungs exhale to the oxygen they consume, starts to shift. When you're burning pure carbohydrate, it sits at exactly 1.0. As fat metabolism takes over, it falls towards 0.7. Researchers measuring this in supervised fasting studies watch it drop in real time. The body is switching fuels, like a generator cutting over from gas to diesel. The ancient human at this stage feels it as fatigue, a heaviness, a slight slowing of thought. Not dangerous, not damaging, just the engine cycling down while the new fuel line opens. Hour 24. The glycogen is gone. This is the line. This is where the real starvation response begins. The liver is now producing glucose almost entirely from amino acids and from glycerol released by fat breakdown. The fat cells themselves are being unlocked. An enzyme called lipase starts cleaving apart stored triglycerides, releasing long-chain fatty acids into the bloodstream. Those fatty acids flood toward the liver. The liver catches them, converts them into acetoacetate and beta-hydroxybutyrate. Ketone bodies, ancient fuel, backup system for the backup system. By hour 24, measurable ketones appear in the blood. They're still low, the brain hasn't fully switched, but the infrastructure is building. Every hour from this point forward, the ketone concentration climbs. And here is something that should stay with you. Pound for pound, human body fat holds roughly 4,100 calories of energy. That's per pound. A lean adult male with 170 pounds on his frame typically carries between 15 and 20% body fat, around 25 to 34 pounds of it. Do that math with me out loud. 25 pounds times 4,100 calories per pound. That is a minimum of 100,000 calories of energy stored in the body of a lean, active, prehistoric human. At a resting metabolic rate of around 1,500 calories per day, that is theoretically 60 to 70 days of fuel. 60 to 70 days. That number means something. It means your ancient ancestors were not fragile. They were tanks built for drought. Built for the failed hunt, the flooded river, the winter that stretched 3 weeks past when it should have ended. If that just rearranged something in your head, good, hit like. It genuinely decides whether this reaches anyone else. Day 2. Hour 48. The brain is shifting. Oliver Owen, a researcher at Temple University, ran a landmark study in 1967. One of the first to directly measure what fuels the human brain burns during prolonged starvation. He catheterized patients who had been fasting for weeks, measuring the concentration of various fuel substrates in blood flowing toward and away from the brain. His finding was stark. By day 4 of total starvation, ketone bodies, primarily beta-hydroxybutyrate, were supplying roughly 70% of the brain's energy needs. 70%. The organ that cannot tolerate fuel interruption for more than 4 minutes was now running almost entirely on fat. This is the reversal. Hold it for a moment, because it changes everything that came before. The starvation you were imagining, the one where the body cannibalizes itself, where the mind goes dark. Where function collapses, that is not what happened to your ancestors over days 2 through 7, assuming they had any fat stores at all. What happened was the opposite. The system shifted. It stabilized. The ketone supply to the brain actually rose as starvation extended, peaking around day 18 according to Owen's data, and then plateauing. The brain didn't starve. The brain adapted. It found a new energy source, and in healthy individuals with adequate fat reserves, it ran on that source with remarkable efficiency. This is what made hunter-gatherer survival possible, not willpower, not toughness. Biochemistry. The Hadza people of northern Tanzania, one of the most studied surviving hunter-gatherer populations on Earth, experience what researchers call a lean season between roughly October and December, when animal prey disperses and certain food sources become scarce. Studies conducted by anthropologist Daniel Lieberman and others at Harvard University document regular periods of reduced caloric intake during these months. The Hadza don't collapse. They hunt harder. They forage wider. The cognitive sharpening from ghrelin, the stable ketone supply to the brain, the body running on its own stored energy, these are not modern discoveries. They are the operating conditions under which our species built civilization. Day 3. The obsession begins. This is where the science gets uncomfortable, and this is where the ancient experience of starvation splits into two very different stories depending on one variable, how long it goes on. In 1944, researcher Ancel Keys recruited 36 conscientious objectors at the University of Minnesota to participate in what became known as the Minnesota Starvation Experiment. These were healthy young men. They ate a semi-starvation diet, roughly 1,570 calories per day, for 24 weeks. The researchers wanted to understand what happened to the human mind and body under prolonged caloric restriction. What they found was disturbing and recognizable. Within weeks, the men became obsessed with food. Not hungry, obsessed, they collected recipes, they read cookbooks for hours, they dreamed about food at night, they talked about almost nothing else. Several men began hoarding objects they couldn't eat, knives, bottles, dishes, as if their brain had generalized the food-seeking drive onto anything that could be held. Their sex drive nearly disappeared. Their concentration fractured. 3 of the 36 men had what the researchers described as psychological breakdowns during the experiment. Depression settled in, apathy, a flattening of motivation that went far beyond simply feeling tired. This is not the short-term ghrelin-sharpened clarity of hour 12. This is what happens when starvation goes on long enough for protein catabolism to begin in earnest. When the body starts breaking down not just fat, but structural tissue. When cortisol stays chronically elevated, when the brain chemistry governing mood, serotonin, dopamine, the entire reward architecture begins to buckle. Tell me, does any of that sound familiar? Not physically, but in the shape of it? The narrowing of attention onto one thing. The hoarding, the irritability, the inability to think about anything else. Which one of these did you recognize in yourself? Go ahead, drop it in the comments. The thing about the Minnesota men is that they were not experiencing some extreme edge case. They were experiencing what millions of ancient humans experienced during prolonged famines. The behavioral changes aren't random. They are a program. Cortical narrowing, the technical term for when the prefrontal cortex hands control over to the survival-focused limbic system, is adaptive. Your brain, under extended starvation, stops spending energy on long-term planning, creativity, and social niceties. It allocates that energy to one task, finding food. Your ancestors didn't lose their minds during famine, they changed their minds, temporarily, into something more efficient for the task at hand. But efficiency has limits. Day 7 and beyond, the triage begins. By the end of the first week, without food, the body has entered what physiologists call protein-sparing ketosis. Fat is supplying most of the fuel. Ketones are covering most of the brain's needs. But the rate of muscle protein breakdown, which was high in the first 3 days of starvation, has begun to slow. The body has recognized that muscle is structural, that structural tissue is not the right fuel to burn when fat exists, and it downregulates the amino acid cannibalization in favor of running on ketones as long as possible. In a 70-kilogram adult, fat stores can theoretically sustain basal metabolism for several weeks, depending on body composition, depending on activity, depending on whether the person is cold, ill, injured, or carrying a pregnancy. Here is where the ancient variables matter. An active hunter burning 3,000 calories a day through movement depletes fat stores at roughly twice the rate of someone resting. Cold environments increase resting energy expenditure by 10 to 30% as the body generates heat. A person who was already lean, carrying perhaps 12% body fat, as many active prehistoric humans did, had a smaller margin. Researchers studying the Hadza found that men typically carry around 14.7% body fat on average. That is not a lot of reserve. Compared to modern Western adults averaging closer to 22 to 28% body fat, an ancient hunter was running on a thinner cushion. The lean ones ran out of fat sooner. When fat ran out, protein became the only remaining fuel. And protein catabolism, the body consuming its own structural tissue, accelerates organ damage. The heart, the diaphragm, the immune system, the gut lining, all of them lose mass. The sequence is not random. Kidney function begins to falter first as blood pressure drops and perfusion decreases. Cardiac arrhythmias appear as electrolytes become critically depleted: potassium, magnesium, phosphate. The heart's electrical system depends on those ions. Without them, the rhythm breaks. The clinical literature suggests that a healthy adult of average build can survive roughly 60 to 70 days without food with access to water, maybe longer in cooler conditions with minimal activity. But survival is not the same as function. By week 3, the person who is still alive is not the same person who began fasting. They are slower. Their immune system is compromised. Their wounds don't heal. Ancel Keys documented that his men, who were not in total starvation, just semi-starvation, lost more than 25% of their body weight over 24 weeks. Their basal metabolic rate fell by approximately 39%, or around 600 calories per day. The body turned down the thermostat to survive. There's one more layer to this. Subscribe if you want to be there when this gets deeper, because next week we're going into what refeeding syndrome does to a body that's been through this. That's where it gets genuinely strange. Roughly, nobody agrees on the exact outer limit for human starvation survival. The Angus Barbieri case, a 27-year-old Scottish man who fasted for 382 days under full medical supervision at the University of Dundee in 1965, consuming only water, tea, coffee, vitamins, and supplemental electrolytes, extended what was thought possible. He went from 456 pounds to 180 pounds. He maintained normal cognitive function throughout. Because he had enormous fat reserves, his body never needed to aggressively cannibalize protein. His ketone-adapted brain ran on fat for over a year. The honest answer about the outer boundary is, we don't fully know. Barbieri is one end of the range. A lean prehistoric child in a harsh winter is the other. The bones keep evidence of where that range was lived. Archaeologists and physical anthropologists have documented enamel hypoplasia, defects in tooth enamel that form when a child's body diverts resources away from tooth development during a period of severe nutritional stress, in skeletal remains from cultures across every continent and every era. Those defects are timestamps. They record the years when food ran out. And they show recovery, the enamel anomaly stops, normal growth resumes the person lived on. The starvation response wasn't just a survival mechanism, it was a survival guarantee. Built-in redundancy. Phase 1, burn glucose. Phase 2, burn amino acids as a bridge. Phase 3, switch to fat and ketones. Phase 4, reduce metabolic rate and ration protein. Phase 5, if reached, the one where organ triage begins, was the one evolution didn't need to solve gracefully, because the ones who reached it often didn't pass their genes forward. The ones who survived wrote the script inside your cells. And here's the thing that lands hardest after all of this. You carry this entire cascading system, every phase of it, in your body right now. The glycogen in your liver, waiting to be depleted. The fat reserves, layered and waiting. The ketone production machinery in your liver, sitting idle. The Ghrelin receptors in your orbitofrontal cortex, ready to sharpen your focus the moment your stomach empties. The cortisol axis, the Harris line-forming bone tissue, the protein-sparing adaptation, all of it. You have never needed it the way your ancestors needed it. Not really. Not in the way that the man crouched over an empty plain 40,000 years ago needed it. Watching snow fall on a landscape that hadn't offered a successful hunt in 11 days. But it is there, running quietly, waiting. What time did you last eat? And what do you think your body is doing right now?